Have you ever looked up at the night sky and wondered if somewhere out there, someone is looking back at you? What if I told you that using nothing but mathematics and statistical analysis, we can actually calculate when humanity will make contact with extraterrestrial intelligence? Not just wild speculation, but real numbers, real equations, and real probabilities. Today, we're going to solve one of the greatest mysteries in all of science. We're going to calculate exactly when humans will meet aliens. This isn't science fiction. This is science fact. And by the end of this journey, you'll understand the mathematical framework that scientists use to predict alien contact, and you might be shocked by what the numbers actually tell us. Let me start with something that will blow your mind. Right now, as you're watching this, there are approximately 400 billion stars in our Milky Way galaxy alone. 400 billion. And astronomers now estimate that nearly every single one of those stars has at least one planet orbiting it. That means there are potentially 400 billion planets just in our galaxy, and our galaxy is just one of an estimated 2 trillion galaxies in the observable universe. The numbers are so staggering that they break our brains. If you tried to count to 400 billion, counting one number per second without stopping, it would take you over 12,000 years. And that's just the stars in our galaxy. So here's the question that has haunted scientists for decades. With so many stars, so many planets, and so much cosmic real estate out there, where is everyone? Why haven't we found aliens yet? Why haven't they found us? This question, this apparent contradiction between the high probability of alien life and the complete absence of any evidence for it, has a name. It's called the Fermi paradox, named after the brilliant physicist Enrico Fermi, who first articulated it back in 1950. But before we dive into the paradox, we need to understand the mathematics that predict alien life in the first place. And that means we need to talk about one of the most famous equations in all of astronomy, the Drake equation. In 1961, a young astronomer named Frank Drake was preparing for the first scientific meeting ever held on the search for extraterrestrial intelligence. He needed a way to organize the discussion, a framework for thinking about the probability of alien civilizations. So he sat down and created an equation that would become legendary in the field of astrobiology. The Drake equation doesn't just guess at the number of alien civilizations. It breaks down the problem into manageable pieces, each representing a different factor that influences whether intelligent life exists and whether we could communicate with it. Let me walk you through each component, and then we'll plug in the numbers and see what we get. The equation starts with R star, the rate of star formation in our galaxy. How many new stars are born each year? This is something we can actually measure pretty accurately using observations of stellar nurseries and cosmic dust clouds. Current estimates put this number at around 7 new stars per year in the Milky Way. 7 stars, each with the potential for planets, each with the potential for life. Next comes F sub p, the fraction of those stars that have planets. When Drake first wrote his equation, this was purely speculation. We hadn't discovered a single planet outside our solar system. But now, thanks to missions like Kepler and TESS, we know that planets are incredibly common. Nearly every star has planets. So we can confidently set this value close to 1. Let's say 0.9, meaning 90% of stars have planetary systems. Then we have N sub e, the average number of planets per star that could potentially support life. These are planets in what we call the habitable zone, that Goldilocks region where it's not too hot and not too cold, where liquid water could exist on the surface. Based on recent surveys, astronomers estimate this number is somewhere between 0.1 and 0.4. Let's use a middle estimate of 0.2. So on average, each star system has about 1/5 of a planet in the habitable zone. Now things get more speculative. F sub L represents the fraction of those potentially habitable planets where life actually emerges. This is where we venture from astronomy into biology and chemistry. We only have one data point, Earth, where life appeared relatively quickly after the planet formed. Some scientists think life is almost inevitable given the right conditions, which would make this number close to 1. Others think it's incredibly rare, a cosmic fluke, which would make it close to 0. For our calculation, let's take a moderate position and say 0.5. Half of habitable planets develop some form of life. Next is F sub I, the fraction of planets with life where that life